Again, good morning, everybody. My name is Sven Bingert. I would like to talk to you about OpenMP. And as Vanessa already pointed out, it could be a simplification in your life when you use threads, or you would like to use many threads in parallel to optimize the performance of your code, of your numerical problem. Then OpenMP is the way to go for, actually. Today, I would like to talk about the most important and main features of OpenMP. Again, this is a long-living standard, was initiated in 1997, and has many more features I actually can cover today. But I think you can at least grasp the idea and could follow on by yourself later on if you're actually going to implement something in parallel using OpenMP. Something else I don't cover today is that in principle, if you have learned about OpenMP and you did already have a session with MPI, you could in principle combine those mechanisms to even improve your code, your idea, your problem solving algorithms, and so on. So the objective today is you should basically understand what is OpenMP about, what can be used for, and where it's actually not applicable. You should learn the basic usage, so by actually doing the exercise afterwards. You should conduct basically simple examples in the exercises, and then at the end you should be able to answer the question, can you benefit by OpenMP parallelization with your actual problem statement? The motivation of OpenMP is that actually there is a large number of problems where it would be beneficial to use shared memory architectures. That means problems where you need compute power accessing the same memory from all compute nodes or from all processes. This is different to what you were taught by MPI, where you have these distributed memory architecture, where you basically compile a binary, you distribute this binary over the system, and then they have a communication between different systems using different memory. And in OpenMP is that you have one big block of memory, and all these threads which you create using OpenMP will access to the same memory. Because there is a lot of these problems, numerical problems, so often it's something with matrix calculations. People are actually still investigating and developing dedicated shared memory architectures or hardware. It's still a process, and people are still requiring it. Of course, the benefit, the drawback is that it's often a bit more costly than distributed memory systems. Nevertheless, it's still something which is developed and actually affordable. Based on the developments, the number of processors available for such systems is still continuously increasing, the same as for the memory itself. The problem, of course, is when you would actually buy such kind of a shared memory system, you will not go for a very dedicated hardware-specific code because you would depend too much on the hardware itself. That's why you look for some kind of a code which is portable, and you know that MPI might be not suitable for such kind of a system. That's why OpenMP is the best solution. It's, so to say, hardware independent. So OpenMP stands for Open Specifications for Multiprocessing. As given at the top, is basically an API to hint the compiler about the parallelizable sections. So you tell the compiler or later on the runtime environment what part of your code can be parallelized easily using threads by giving statements in your code. These statements can be ignored by some compilers. Some compilers would accept those and would try to parallelize the code based on your hints and your directives to the API. The OpenMP is basically a standard which is further developed. So the last, I think, is November 2021 with the version number 5.2. But at the end, it's just the definition of the API. And at the end, it has to be implemented by the compiler. So there's different compilers. We actually implement this. So today we will mostly talk about Intel compiler, but of course you can also use GNU compiler or C compiler, but you can also Fortran compiler and so on. As it is, so to say, compiler dependent, there might be some differences, which of course are not for the main functions as we discussed today, but at least there's support for GNU compiler, Intel compiler, Visual C, and so on. So in our examples, as I use mostly C, but as given here, Fortran would work also. But I think nowadays people are more used to learn C in their studies. So actually, when I did my PhD, I was using Fortran 90 quite extensively, but together with MPI and partly OpenMP. So OpenMP again is basically meant for shared memory systems or architectures. You could combine with MPI. So say you distribute your binary to a node in the shared distributed memory system, and on this dedicated system or this one node, you could do an OpenMP job using the memory of this one node. At the end, if you look at MPI, OpenMP, and I will come back to this statement at the end of the lecture, it's not doing too much magic. Yeah? It simplifies the life against using pthreads, but at the end you have to be very careful because you can also have deadlocks. You have to synchronize your I/O access and so on. And the challenge for today is basically that you also do some mistakes where you actually learn how difficult or what problems could actually occur if you use OpenMP and you're not aware of having deadlocks or problems with accessing memory at the same time. So the OpenMP building block, I would say, consists of 3 parts. And again, here I talk mainly about C code. Later on, there's one example about Fortran code, but nevertheless, at the end, it all looks pretty similar. In order to use OpenMP, you need to have directives. That's the first part here. I try to use my pen. You have the directives, which is this part here. So you have at every directive, you start with the pragma OMP, so for OpenMP, and then you have the dedicated directive, which is here actually called parallel. The other part is called a clause. We will come back to this later. But the end, always start with the hashtag pragma OMP and then a directive name. And what kind of directives are existing, what they are used for, you will see in the next slides. As you can guess already here, so parallel basically states for going for a parallel section. OpenMP comes with a set of functions which are, so to say, given by a library. The library should be, so to say, included in your code. In C it would be like this, include omp.h. And then you have access to dedicated functions like OMP get num threads. Based on the name, you can assume or guess that it's the function to get the total number of threads which are currently available for this process. It returns an integer, so it's a number of threads. And the last part is you can set environmental variables, or environment variables, usually with the command called export omp num threads, here equal to 8. So this would be if you want to use 8 threads for our OpenMP parallel parts. There's some benefits of using environment variables. You can put it in your bash RC or profile file to actually automate your processes. If you're going to share, if you're going to use OpenMP together with MPI, of course, get more complicated. You have to make sure that this export is also executed on all nodes where you would like to use OpenMP. The number of possible environment variables is large. This year is only an example. It's easy to test, and I also encourage you later on when you do your exercise, please try to use such kind of environment variable and compare it with the library function where you set omp get num threads, or set num threads actually. So omp num threads would actually set the number of threads, and there's a similar function in the library to be used. A hint here to compile a code where you use such kind of directives with the pragma at the beginning. And I hope you have all used in the meantime our infrastructure at GWDG or our HPC system at GWDG. There is different compilers available. You can switch these compilers with module. And we use here the GCC compiler or the ICC compiler. And there is to compile with GNU compiler, it would just be using the flag -f OpenMP. And for the ICC compiler, it would be the flag -q OpenMP. This no multi-byte characters. I think this is a bug of my shell. I'm not sure if you have to use it, but I keep it here just for myself to remind me that I have to check this properly. So if you're going to do later your tests and you compile here, just keep in mind that you basically work on a front-end node and you're not submitting anything to the HPC system, so you're not using the queuing system. So don't use too many threads, but I will come back to this later. Okay, there's sometimes I switch between the slides and the chat. There is a question by Lukas Friedrich. Yes, there is some stuff where you can actually, oh, there's also links here. Sorry, Pia put a link here. Yeah, you can combine Python with OpenMP. But I think we should start first going for OpenMP first, and then and if you're interested, we can talk about this later again. So a very simple example how in parallelized code using OpenMP would look like. This I think is almost the smallest example, the standard Hello World example. Basically what we do is we use the OpenMP library. We start our main function in C, then we have the pragma OpenMP parallel, and then we have printf Hello World. If you would compile and execute this, the output would look more like this. So the binary is called .hello, hello, and the output would look like this more or less. Why more or less? Because in this output, I would assume that I used 4 threads. That means in the pragma OMP parallelization section here, a dedicated number of threads are created given by either a function before, which is not existing, or by the environment variable, which you don't see here, or it will use any system defaults. That means if this is using system defaults, it could be that it uses the number of cores available for this binary or for this process, and then you would have here hello world printed out in the order, the number of cores available for this process. So you should steer this. Basically, you should not let this unknown, so to say, try to have control over everything or most of the things. So you should put somewhere the number of threads to be used in your parallel section. How does it look like if you look on a thread level? So what is used is called the fork join model. This picture is actually taken from the OpenMP tutorial page. So in OpenMP, you have something which is called the master thread, which is the thread which is alive during the full lifetime of your process, of your code, from start till end. And you can start in the lifetime of your process different regions, parallel regions with different number of threads actually. So as you can see here, there is 3 different parallel regions created, where we have 3, 4, and 2 threads accordingly. After each parallel region, it collapses back to the master thread, or at least the recently spawned process threads 2, 3, and 4 are actually deleted after this parallel region, but not the master thread, of course. The master thread will contain and continue furthermore till the end of the process. The threads in such a parallel region are called teams. Even the master thread is part of the team, so you have to be a bit careful. And usually you have a barrier at the end of each parallel region. That means that at this point where it collapses to one thread to the master thread, you have some kind of cleanup of memory and so on. So every thread which was created will have to synchronize in time at this point after the parallel region. So actually here and here you have basically a barrier. At the end, of course, the master thread will also die out. So it's important to see that it's quite helpful that you can control the number of threads by, for example, using the library function OMP set num threads, and you can just start and stop parallel regions as you want. If you would like to do, so say, a work sharing, so you have many threads, there's two typical examples you would go for. The first one is the classical single instruction multiple data, SIMD. I think you have seen that before. Here in the picture it's depicted that you have the master thread is incoming, then you fork into a team of threads, then you do some fancy stuff, and then you join back with the barrier here to synchronize back to the master thread. A classic example is you have a vector where you just add a number. So you have this instruction is called adding a number. It's maybe a fixed number, and you do it for all elements of the vector. So you have multiple data, so all the elements in the vector. Then it's single instruction, multiple data. And this is the most easiest example. It's quite easy to parallelize, and it's just one command basically in OpenMP. This might be useful for many problems in your code or many parts of your code. Sometimes you actually have to go for something else, which is then the multiple instructions for multiple data. So you have the incoming master thread. You create a set of threads then, but you want that these threads are doing different things. Yeah, so you have different instructions for different data, so multiple instructions, multiple data. This is doable also in OpenMP. It's actually called sections. It's really, oh, sorry, I cut through here in the middle part. It's called sections. With these sections, you can control which thread is doing what part of the code. And as you can see, a thread without any section would just pass by and would wait at the barrier at the end of the parallel section or the parallel region to wait to finish all other threads. This is also a bit more complicated because you have to think about what kind of code actually needs to be parallelized and Yeah, and to make this equivalent in size, so to say, I would also say, because if you would have one thread doing quite long calculations, all the other threads still have to wait for this one thread. So doing here a parallelization of your problem is more difficult than in the SIMD example. In MPI, message passing interface, you learned that communication is quite important. You basically did the communication by sending messages between processes. The messages contained data and sender receiver addresses and so on. In OpenMP, the communication is mostly is done via shared variables. Yeah, so if you want to communicate information from one thread to another, you have to use a shared variable which is seen by all the threads. Yeah, so one thread is storing a number in a variable which is then later on read by another thread. That would be the way how you communicate in OpenMP. So again, the master thread, the execution context exists during runtime. For the worker threads, so the other threads in the team, the execution context exists only during the parallel section. So when the threads are spawned, there will be a dedicated space in memory for the code execution and for the variables. After the parallel region, this is of course deleted and cleaned up. So speaking again about the shared variables for the communication, because you would like to actually improve your code and speed up, not all variables need to be defined as shared. There is also a keyword called private. And as I will show you later on, so when you declare a variable in a parallel region, you should declare it. There is basically the possibility to say it's either shared, private, or none. So if you don't specify a variable in one of these clauses, which I will give you an example later on, it will be by default shared. And this, so say, brings some difficulties or some problems, because if you forgot to specify a variable which should be private, then it will be shared and your code will crash, or your code will not produce what you expect. But this kind of problem or error is really hard to debug. Yeah, so if you have a code which doesn't behave as you expect, only due to the fact that the variable is shared instead of private, it's really difficult. That's why I really recommend, later on you will see an example, put every variable in either shared or private clause. There's a third option if you have a variable which is, so to say, to be reduced at the end. That's why there's a clause called reduction. Then that means that, so for example, you have a variable a, and at the end of the parallel region, you would like to have the sum of all variables a of all threads. Then you can use a reduction with the operator plus. If you use reduction as an attribute of the variable, then it's implicitly private, because of course every thread might have a different value for this variable. If you have shared variables, every thread has access to the same memory space. So you have to be careful in order writing and reading. If you use variables with a private attribute, copies of the variables are created at the beginning of the parallel region. Here it's again the same. So and here, as we marked in red, this is also a problem for any other code which is not parallel. But so if you have a private variable, so which is created at the beginning of a parallel region, it is mostly undefined at the beginning and end of the parallel section. Yeah, so you declare a variable as private, and then you get memory allocation for this variable, but the status of the value is undefined. This brings me back to the point that it's always the behavior of your code and your parallelization in OpenMP depends on the environment, the system you use, and the runtime environment, and the compiler. So for some compilers and environments, you have automatically assigned zeros for all undefined variables, which also might depend on the compiler flags. So if you use specific compiler and use -03 optimization, it could be, I'm not sure, actually I did it a long time ago. But you can control the compiler to tell that every variable which is not initialized properly in the code should initially be initialized with 0. But in principle, just to make sure that you don't do any coding error, assume that every private variable is undefined at the beginning and the end of the parallel section. Except, of course, those which are owned by the master thread. So when using shared variables, as already mentioned, you have to avoid concurrent writes, because they all access the same memory. There is a mechanism which is a bit more complicated. I will think there's a slide at the end that you can try. You can create spaces in the memory for each thread, so you can still have different copies of the shared variables. But this brings another problem of having synchronization after the parallel region. In principle, all threads access the same memory, so you have to avoid concurrent writes. So it means that one thread might read while another writes, and this, of course, leads to an unclear state at the end of the parallel section. Again, this is a problem, hard to debug when you run your code. Here, memory cache can be used to avoid conflict, so you can create a cache for your thread where you can have, so say, a copy of your shared variable, but then you have to use some kind of flush directive to enforce consistency between these threads. There is no example in the exercise later on for this, just to point out that there's ways to deal with this problem. Let's talk about a bit more complicated problem. Let me quickly look at the chat. Any news here? Okay, nothing in the chat. Right, let's look at a bit more complicated code. Again, we start with including the library on top. We have our main function in C. Then we have two integers created. Actually, there's not initialized properly. Nevertheless, two integers. And starting from this line, we actually want to do something in parallel. That's why we tell the compiler, here we should have a parallel section. And we tell the compiler that we have a variable TID, thread ID in principle, which is private. That means we have copies of thread ID in the memory. Again, here, based on this code, I don't know how many threads are actually available. Depends on the system, environment variable, and so on. Nevertheless, the code works. So then in this line, we ask via the C library the current thread ID. So get thread num returns the number of each thread. As I mentioned already before, we have, so to say, the master thread, which has the thread ID 0. And we have the worker threads, which have then numbers 1 to n, if you have, n minus 1, if you have in total n threads. So with this line, you ask for the current thread number, which is stored in the variable TID, and you print out a message with this ID. So basically, in this fork join model, in this line here, you do the fork part. Yeah, from here you fork n number of threads. In this line, now you have the possibility to know which thread is the master thread, basically the one which has the TID equals 0. That means the block below is only executed by the master thread. The master thread would ask OMP get num threads. Is also a library function. So he asks, so say, for the total number of threads available for this parallel region here. So this is a parallel region coming from here to down. And then he would print out the total number of threads on the terminal. And at this line here, basically, you end with your parallel region. Means after this line, we have a barrier, an implicit barrier, where we, with this bracket, we have an implicit barrier where we have to wait for all threads to join, and then the code will continue. Important here is that if you start with a, I change the color, pen color. So if you start here with the parallel directive, you do a fork of threads, and only the following block is executed in parallel. Here we have two brackets which define the block. If you would have only one command but not a bracket, only the concurrent command would be executed in parallel and then returns back to the non-parallel region. I think to compile and show the example is something you can easily do by yourself. I think this code is also in the exercise, so please go ahead, compile, test it with different number of threads by, for example, setting the environment variable, or by adding a line here before the pragma. So if you would like to set the number of threads, you have to do it here before you spawn the threads, of course. In another example here, this is not the full example because we don't have this library and this main function anyway. So we have here two vectors, A and B, which are initialized with numbers from 0 to n minus 1. And then you have here starting again a parallel part. So at this line you fork new threads, but now you have to say not only a private variable I, but you have also shared variables A, B, and C. I would like to stress here that if you look at the code, so n is of course only part of the for loop, we don't care, but A, B, and C are actually, also A, B, and C are, C is not defined, should be above here. A, B, and C are vectors which are shared, so every thread can access to it. And there's a private I, which is, so to say, undefined when we start the parallel part. So here we start the parallel part. So you have to find the according bracket. I think this is the last one here, and here you end with the parallel part. But what we do is, let me change the pen color. We do a new command directive for our MPI to say we would like to do a for loop in parallel. I will come back to this later anyway, but just to tell you, what happens is that this concurrent loop, which is directly after this for directive, will be splitted up according to the threads. So you have here, in this example, n iterations of adding numbers here. And these n iterations are splitted up, and each thread will get a certain amount of these iterations to execute. For a simple example, if you have two threads, the first thread could go from iteration 0 to n-half, and the second thread would go from n-half plus 1 till n. So roughly. How the threads are actually distributed, or how the iterations are distributed to the threads, so first half, second half, and so on, is defined by the clause which is called schedule. And the schedule even has a parameter which is here dynamic. Also, there's a slide later on about this, just to hint. Dynamic means when a thread is done with the iteration or some iterations, the runtime environment will decide which next chunk of iterations will be assigned to the thread. Here, the brackets are not correct actually. Fear. Sorry for the missing brackets here. So here we are done with the for loop, yeah. And then afterwards we are still in the parallel section, so we are still having the threads available, even though they are done with the for loop. We have a new directive which is called master, means that here only the master thread enters the code block below, and all other threads will actually wait until this is done, and then they would join afterwards in the barrier to finalize the parallel section. That means the second for loop here is actually executed only by the master thread, and the master thread would actually print out the vector C, which is calculated in the parallel part above. As I pointed out here, schedule have different parameters. I will come back to this later. There's the option no wait. That means that so I can put it at the for loop. That means that threads are which are ready. I can go back here. If I add no wait to the for directive, threads which are already done can continue to the next code and don't have to wait for the other threads. So no wait can be placed at many different other places. It would just allow threads to continue and not being stuck in a barrier. Then other examples, we can so they control the execution of a for loop. So basically, we can ask to be ordered, and that means that iterations must be done in the same order like they would be executed in a serial program. Yeah, and here you have two examples. Here, ordered is actually a clause for the directive for, and here is ordered a directive. Okay. So from the directives, you have learned already two main directives. The one is parallel, so to start a parallel region, and for to start a parallelization of a for loop. But there's others like sections, singles, and task, and so on. And we will talk today also about section singles. Single. And of course, there's many more. And if you're interested in doing OpenMP development or code development using OpenMP, you should check what other directives are available. For synchronization between different threads, you can use barrier. There is something called critical, master, atomic. Again, we will have part of that covered here in the lecture. But there's also something which is can be used to control the data space, which is then called thread private, and we can come back to this in another slide. Here's the promised example of two different languages. On top we have the C code. That's what you've seen before. You have the OMP and then any directive, and then you have a list of clauses. That means, for example, the schedule, ordered, and so on. Some clauses might even allow variables or values to control the clause. And important is that is only every directive only is valid for the followed structured block. That means in C, the structured block would start by curly brackets or a single line. For Fortran, for those who are doing Fortran development or Fortran 90, you see on the bottom part, it looks pretty similar. You have OMP, directive, the clauses, a block, and in difference to C, because in C you have this closing bracket, in Fortran you don't have this. You need to say OMP end to close the parallel region properly. You will learn it quickly, but just to hint, so do less mistakes. Directives are written in lowercase, or everything in this Pragma here is actually written in lowercase. For the clauses, we had some examples already, which are for the data space. We talked about that we have the possibility to say that we have a list of private variables. You can have a list of shared variables. But you can also define that something is by default either shared or by default none. So neither shared nor private. You cannot say by default private, this is not working. The compiler would complain. But you can put shared here. And as you can see here, you can combine. You can say in the example below, you have one private I and the rest is by default shared to simplify life. Again, I would recommend that you really list all variables by name in either private or shared clause, just to circumvent any problems with the code. Because if you have to put it by hand, you have to think about if it belongs to shared or private. If you just say default shared, you might miss one which should have been private. So the reduction operator is given here. That means in this parallel region, which is started here on the top line, we have a variable called result, which is implicitly private. And as you can see below, again, we have a for loop which is parallelized. Ignore the schedule clause now. That means the threads will work on different iterations. So to say that result is, so to say, handled by each thread itself. So there's a copy of result for each thread. But importantly is that here after the parallel region, we have the sum of all result variables in the variable result of the master thread. The master thread have the result in here. Why is the sum? Because the sum was defined here in the reduction clause. I can change color again, maybe easier to see. So here I have the plus sign saying reduction plus. You can have here different other operators like minus, and I think there's something larger than, and so on, also getting the greatest and so on, or the greatest value and so on. It's a bit similar. I'm not sure if you learned about this in MPI. You have also reduction calls where you collect from different partners in the communication and reduce it to a sum or something similar in one variable. The code is, as it's given here, basically correct. What I would point out here, I would, in this case here, make sure that the result is somehow initiated. As I said before, the private variables usually are not initialized, so they're undefined. And if you start your calculation with result equal result plus something, you might have an undefined state. Or you use a compiler flag saying all undefined variables needs to be initialized with 0, then this is safe. So depends on the good practice of programming how you solve this issue here. Okay. Undefined variables. So variables declared with private are undefined at the start end of section, as I already said. So what you can do is you can use the first private clause, which is with a list of variables, which is to say you hand over a list of variables. Means that even though it's a private one, which it will be initialized with a copy of the same variable existing before the parallel region. Yeah, so you need to have the same variable in your code already with a given value. And if you then start your parallel section, you can say first private, and then you initiate the copy with the value of the first appearance of this variable. And then, of course, as it states here, the first private, it's then still private afterwards. Right. I talked already about functions, library functions. Here is a list of library functions which are quite common. So in the first one, in parallel, you basically ask in your code, am I within a parallel region? So if your code gets larger and larger, you might not know if I'm currently in a parallel region or not. The return value will be true or false if you are within a parallel region or not. The second one, get num threads, we had it before, is where you can ask how many threads are actually available in this parallel region. As you said, you can have different regions with different number of threads. In the third, you can have the thread num get the number of the thread itself, which can be useful if you have some logic where you know which thread needs to do what kind of task. So for example, if you know how you split up meaningful given matrix or whatever. What you can also do, you can put znum threads before a parallel region, so to control the number of threads available for this parallel region. Now this is a command. If you don't use environment variables, I would actually recommend to use this function to specify the number of threads in your parallel region. I can make it red. Okay, then I will skip the next one, maybe come back to the later, but as it is the task to optimize your code and to save time, you are interested actually in the wall time. There is a library function to call the current wall time, and if you do it twice, you can calculate the speed, the runtime of the code, or the part of the code you're interested in. The lower part with the lock, I think it's pretty similar to p-threads, where you can just say manually lock specific things, and I would actually skip this here because it would be too much for today. Coming back to the time measurement, there is this OMP get W time. The return value is a double, and it basically returns the time in seconds elapsed since a fixed point in time in the past. The temporal resolution is limited. That depends, of course, on the architecture and the operating system you use. But if you're interested in the elapsed time between 2 points in your code or 2 lines in your code, you can call this function twice, and you just compute the difference, and then you don't mind about the point in the past actually. Yeah, then you have just the delta of time which is used for your code. And it's of course in seconds then. Yeah, so if you call W time twice, and then you get the time of your code. Here's an example. So you start a parallel region. In the first line, again here number of threads is unclear. You have maybe some code which is before, but actually here you have your code of interest. So what is how performant in this part here? And that's why you are interested in measuring this part. That's why what you would do is basically you would first call W time to get the starting time. And afterwards, you would call again W time to get the end time. At the end, you print out end minus start to have the time in seconds in total. So what else do we see here is that we have again a different directive. It's called a single here. That means only one thread is required, is allowed to execute this line. Yeah. It doesn't have to be the master thread, but basically only one thread should go for it, because you need only one thread getting the time. That's sufficient. And the same at the second part, you would say only a single, because only one thread needs to get the second time, and then you calculate the difference. What else we see here again? So we have here again no wait, because if you don't put this here, basically other threads would wait until this single thread would get the time, and then they would continue afterwards with the code. So you can here speed up a bit if you let pass the other threads directly to the code of interest. Meaning, an example again, so if you have 16 threads created up here in the parallel part, oh, it's not a nice 16. 16 threads started here. One thread would be here, and again, 16 threads would actually do the code of interest here. Yeah. Because we didn't change anything of the parallel region here in this code. So there is now a few more slides which I actually would then do after the lunch break. Not so many slides left, but we would go actually for the loop parallelization. Let me check quickly the chat here. Maybe I missed something. So Johannes wrote, but if it is set to 0, how can the boundaries work? I understand that n changes, but for this loop would mean that during the thread run it overrides CJI several times. Johannes, I'm not sure which slide this was. Let me quickly go back to see if I can find it. You mean this slide, I guess. So n is not changed. So n is yeah, actually, n should be specified basically here in the shared private of the parallel region. N is fixed, but for so if n would be 10, and we would have two threads, the first thread would go from 0 to 4, while the second thread goes from 5 to 9. Is that understandable? As it means that the first thread goes in through 0 to 4, the first 5 elements of A, B, and C, while the second thread will work on the but I equal 0. Yeah, I will be changed. So basically, that because it's private, and this directive 4 tells each thread at which I to start. So not all threads start at I equals 0. So thread starts on a given I. And depending on your schedule, it is sometimes even unpredictable which iteration number I are assigned to a thread. It's sometimes done by the compiler, sometimes the runtime environment. It's really depending on the schedule you do. Yeah, the schedule can be different. If it's static, you would basically divide the full iterations. So you have n iterations and you have 10 threads. Then you would divide the n iterations in equal size chunks of iterations, and then you share these iterations within the threads. So every thread will have different starting I and ending n, so to say. No, so Maike wrote it's the first thread, it goes from 0 to 9. No, it's as I said, so the start and end of each thread is given by the schedule clause. And this is the strength of OpenMP. You don't care. You just say, my loop has a given length, let's say of 10, or let's make a bigger number, of 1,000,000. And you can come there with any number of threads, and the runtime environment will make sure that these iterations, these 1,000,000 iterations, are distributed among the threads given there, having different I's and different N's. So is the order of threads chronologically by I, or can the threads have a mix of I? As I said, the schedule. That depends on the schedule. So after the lunch break, we have, I think, another slide about the schedule. But I can also say now that in the static example, you would make equal size chunks of iterations. So 1,000,000 divided by 10 would be 100,000 iterations for the first, 100 iteration for the second, and so on. But if you go on a dynamic level, you would put a chunk size of 1,000 to thread 1, 1,000 to thread 2. But if thread 2 is already done, he will get already the next chunk. Yeah, so the runtime environment will decide what chunk of iterations will be executed by which iteration, if it's the schedule dynamic. So Johannes got it. I hope Maike, I'm not sure if I pronounce your names correctly. If not, I'm sorry. I try my best. Maike is still typing. No, it's not. You don't. Maybe you know you mean something else, but the amount of threads doesn't depend on the value n. So you define beforehand how many threads are. You define the real value of capital N, and based on the schedule clause, let's call it n prime. Based on the schedule clause, how many times the for loop runs? The loop runs only once. Let me try something. Can I skip here? Discount the annotations. Okay, now you understand, Michael. But I can still just show one picture. Then we go for lunch break. That makes it even more clear, I would say. This picture, I think, explains it quite well. So you have here on the bottom line 200 iterations, and you have on the left, on the vertical column, you have thread ID, and you have 3 different kind of schedules. In the static part, you have equal size chunks, so each thread will have 50 iterations. In the dynamic part, it's unpredictable, depends on the speed of the thread. And there's a guided one, which I will, so to say, later on explain a bit more about guided. But this is, again, this is, so to say, the very strong benefit of OpenMP, that basically, so at least on many codes I know, and the code I use is that we do quite basic programming. So all is on a level of for, if, and case statements. And so that means you have quite a lot of for loops. And if you find a mechanism to easily and flexible parallelize such kind of for loops, then you can gain quite a lot of performance. And as I said here, it is here independent of the number of threads. Yeah. So you just put your loop there, you know how much iterations you need in total, and you let just the system decide how to get through this loop as fast as possible, having n number of threads, lowercase n. Okay, then based on the time schedule, we have now a lunch break. Jonathan is still here, so maybe can you point out if I should stop the room, or I think the room will will continue. I will stop the recording now. Okay, recording started. Let's continue with a few more slides before we start with the exercises. I already shared the screen. I hope you can see the slides. If not, just raise your voice and I can fix it. And so we stopped at the question about the loop iterations. And this is, of course, was a valid question, and it's important to understand. And so we have to really point out that this is the strength of OpenMP, yeah, this loop parallelization part, as I mentioned before the lunch break. Because many things you will express as loops in such kind of a code. Of course, it always depends on your code and your problem and your language you use, but for the very basic stuff, I think this is true. And as I said here, each thread will work on a subset of the iterations, and the subset is, or the chunk is defined by the schedule. And this is, when we do this classical for loop, it's a SIMD operation. So we have one instruction in the loop and multiple data. And there is, beside the schedule clause, also other clauses like ordered, if, order, copy in, and so on. And again, I will cover part of these clauses here. So in the white box, you can see again the how it's written in the code. So you have the OMP4, then bracket the possible clauses afterwards. Again, important to note here is that only the directly subsequent loop is parallelized. Yeah, we will see in a second here an example. So in the code example below, you can see there's a list of loops. And if you have only the for directive, then only the first, sorry, that don't cut through. Only the first loop will be split up to the threads, not the other three. So important to note again here is that we have three different directives here given. So you have the OMP parallel directive, which is just splitting up into a number of threads. It starts a parallel region in the code. And so you know after this call how many threads you have. And then if you have done this, you would basically in the second step, or within the parallel region, you could start a parallelization of a for loop using the existing threads given by the above command using OMP parallel. So if you want to use OMP4, you have to use OMP parallel before so that you have at least a parallel region. And again mentioned that only the first loop is actually parallelized after the OMP4 statement. That's also true for a combined version, and this is smart to use. So if you have just a for loop to parallelize and no other code, you can combine the parallel directive with the for directive into a parallel for directive. That would be basically do both in one go. First, create a number of threads and use those for splitting up the iteration. So I would like to erase this here, that. I can't read. Okay, then you have, if you have such kind of a structure of nested for loops, as given here in the code example, you can use a feature which is called the collapse, which is a clause again. So a clause for directive 4. With this collapse clause, you can, so say, speed up and even distribute the iterations of many loops into many threads. This works only if there's no dependency and you're not allowed to have any code in between these loops statements here. No code allowed here and no code allowed here. If you have such a structure and you have no dependency in your operation, in your instruction, then you can use collapse and it will sort of say compute how many iterations in total there are. So you have here 10 times 3 times 7 iterations, and these would then be splitted up to the threads in total. So this works only if there is no code allowed. It's actually a rare use case, but it can happen, and then you can use the collapse function. Other words you can use, other clauses. You have the OMP parallel for ordered clause. That means that threads of the team execute the ordered region sequentially, basically following the order of the loop iterations. So this is sometimes necessary to avoid conflicts. The question if you actually gain any benefit in speed up, sometimes not. If you have OMP for schedule, the clause schedule, that's what we discussed before lunch break. You can hint first the compiler and the runtime environment how the iterations of the loop can be distributed among the threads. We have here 5 different possible keywords for the schedule. The first one is static, meaning that all iterations are split up in chunks. with equal size. Yeah, again, you have 100 iterations, then you have chunk size of 10, for example. And then each thread will get assigned a chunk. If a thread is done, he will get the second chunk, and so on until it's done. Not necessarily that you have the same amount of chunks as threads. The chunk size depends more or less on the problem. That chunk size is, I don't know, it's the runtime environment. It depends on the runtime environment. Yeah. So chunk size is not given by the number of threads, but it's equally distributed if you use static. You can control the chunk size if you put a keyword chunk after static with a given integer number, specify how large the chunk is. I'm not sure if you have an example in the exercise, but I think it's not important to play with today. So interesting is the dynamic part, is that so each requesting thread gets a chunk. Again, here you can control the chunk size, but the order is more random. So whenever the thread is done, it will get the next chunk. In the guided example, I think if you wait for the next picture, the chunk size decreases with iteration. So you first will start with large chunk sizes for each thread, and then you decrease toward the end of the number of iterations. In the runtime environment, you completely hand over the control the runtime environment. In the runtime schedule, you use the environment variables. So you can use guided, for example, as a schedule keyword if you specify it in your environment variables. So in other words, so you can put runtime as a keyword for schedule all over your code. And just by flipping the environment variable before you start your code, you have control over all places where this schedule is used. So you don't have to modify any place where you use this specific schedule. It gives you some freedom, or it simplifies some testing at least. And in the last part, the auto part, the compiler takes over and the runtime takes over the it takes over the control over the distribution of the chunk sizes. Here again, the static part. Here's the chunk size. In the end, each thread will get the same size of iterations. In the guided part, you start with the large chunk size, and it becomes smaller towards the end. So why is that? Because if you compare static with guided, it could happen that even though they have the same number of iterations, one thread might be slower than the other thread. Doing the same operation or instruction, the other threads would have to wait for the single one which is too slow. And you don't have control over that. In the green part, so say you control the speed a bit of the threads. So you start with the large iteration number for each thread, and then you look how fast each thread is, and when you so say make your chunk sizes smaller and smaller toward the end, you can so to say a bit control that, if possible, all threads end at the same time. That's the idea. So that the finish time of all threads for the loop is almost the same. This is why guided is quite useful. And then the dynamic part, as you see here in the picture depicted, you have different distribution just depending on whenever a thread is done with its chunk size of iteration, it will be assigned a new one. So let me check nothing in the chat. So parallel sections. That's a feature I mentioned at the beginning that is very useful for multiple instruction, multiple data operations. You can start a parallel section with these pragma OMP parallel sections. In this region, you would have to specify several single sections by OMP section, but you will see an example in a second. Important to note here that each section is executed by one thread only. Yeah, you have a section defined, and one thread goes into the section, does the task, and returns. That's why this is good for small tasks. They don't have the problem of that one task, one thread gets too slow. And the other problem is then if you do this, usually the order as the execution of each section is not well defined. So you don't know which comes first or which prints out first, which saves first, and so on. So if you do fancy stuff with memory, you have to be careful. Here's an example code for using sections. You have at the beginning again an initialization of a vector A and a vector B. Then you have here started a parallel region with a given number of threads. You have A, B, C, D as a private variable. As a shared variable. I is private. And N is missing again. And then after this split up of your parallel region, you would say you need to have sections. This is line. Yeah, you just say there will be a n number of sections coming afterwards. In this example, we have two sections given here. So one is here, one is here, and independent how many threads you have up here, one thread will go into the first section, a second thread will go in the second section. And then they do calculations basically. C is the sum of A plus B, and D is A plus A times B. So different calculations. So it's multiple instruction, multiple data. Yeah. Okay. Other directive to be used is the master directive. So only one that one part of the code is executed only by the master. Something is critical, that only one thread allowed at a time. That doesn't have to be only one thread allowed at a time, but all threads will actually go through this code. A barrier, also from MPI, and we talked about this today, is a position in the code where we have to wait for all threads to arrive. And flush is used to synchronize, so that basically the memory is cleaned up and shared and so on. The idea of parallelization is to distribute the workload, and we had this critical section which I mentioned before. But we also have this single directive, OMP single. This is useful for tasks within parallelization to be executed by one thread only. Yeah, so if you have to do I/O operations, for example, and usually this is done by one thread only. Often people use, for simplicity, the master thread, and then they say if thread ID equals 0, then do the operations. But here you can just say let the runtime environment decide which thread is doing this. And the difference between single and critical, again, is that in single you have one is doing this job, and in critical one after another. So it's just to avoid race condition. One thread after another is executing the block of code after the critical statement. So at some places, as I mentioned before, you can use no wait to allow other threads passing by sections or single directives. Now I would like to point out a problem if you do coding which is a bit more complex. Here you see the main function, which, so to say, uses the command line arguments, and immediately after that you start a parallel region, so doing something in parallel, where we actually started a state that two variables, my start, my end, are private. So in this case here, you would first define, you would initiate the two variables by calling a function get my start, get my end. These are calculated, so say, by using OpenMP get thread num and get threads and so on. But important is that afterwards there's a function called work, which is defined here above. Change the color. So here on top we have defined the function work. And this is called within the parallel region of the main function. The problem here, if you do it like this, so you don't have any parameter in the function, that here my start and my end are not well defined, even though they are here globally defined as integers. So this will screw up your code. Yeah, in this case, because you set it here as private and end for as a start and end are private for the threads, in the work function these two variables are not well defined. And this is also hard to debug because this function might be placed somewhere in the code, not as close as to the main function as given here. There's two ways to circumvent such a problem. The first one is you do this. I'm sorry. Yeah. The first one is you do the same as before, but you would hand over the private variables as parameters in the function call. Then they would be in here, and then they would be defined. It's a very common use case, but there is something offered by OpenMP. So this is the thread private clause here. That means after you created, or after you call the variables, you can, so to say, define them as thread private. That means that that a copy is created, and we had this before, and so to say that this thread, that these two variables are actually defined as a copy for each thread in the work function. Yeah, so again, the work function here would be without parameter, but as you defined thread private for start and end, you would have the correct value in these two variables in the function work. Okay, then we're already done with the slides. We have some exercises here that I created 2 blocks, exercise 1, exercise sheet 2. There's simple tasks where we just go through more minor changes in the code. There's some more complex tasks, so feel free to go through in your own speed. We will discuss them, and I would be actually happy if you actually contribute and present what you think is the best solution. So I'm not sure how the other speakers did it before, if I have to show all the proper solutions, or if you could actually show what you did and why you did it and so on. So it's easy to share a screen here. Not everybody is connected with audio. Maybe you can reconnect using your audio. But that would be highly appreciated if you could actually show your code and tell us what you did and why you did it. The exercises are downloadable on the web page. I think you did it already. I placed on the first exercise 2 references, 2 URLs. So one is the OpenMP specification, the other one is a tutorial. Basically what you need is to go through is the slides I showed today, and I guess the OpenMP specifications would be sufficient. There are some questions without actually coding to do, but they are there to see if you are able to answer the question, then you understood what the lecture was about. And of course, if you have any other idea and you would like to quickly set up your own numerical problem, I'm pretty happy to listen to your ideas. Yeah, so that's I looked through and I came up with Sudoku. So I have a code which solves Sudoku, which I used as an exercise to parallelize. But standard stuff like computing pi and so on is available on the internet in masses. So if you have any other idea what could be parallelized, so please let me know, and we can discuss it, and you can show me ideas and so on. Yeah, so I'm happy for every contribution. Okay, then in the slides you can find also some references here. Again, you have here the OpenMP specifications 5.2, and there is yeah, and the bottom part is the tutorial which I linked also, but this should be also in the exercise session. Okay, that means now that if I understand correctly, and Jonathan can maybe help me and guide me, but you would now switch to the other big blue button room where we have the breakout rooms. Then you go into your breakout rooms, and I'm going to visit you in the breakout rooms to see what you're doing, ask questions, or you can ask me questions, and then we discuss it. And then we reconvene back before the small coffee break, which is at, I have checked the timing. So it says short break. Oh, there's no break. But I should make a 10 minutes break, I would say. Where is my slot? Oh, Thursday. Here, 15 o'clock. Okay. So at 3 o'clock, we make a short break. Oh, we should do it earlier. Sorry, it's wrong. So if we have now 1:30, we go till we have left 2.5 hours. Is that correct? 1 hour 15. So we make a 14:45. So we make a break at 14:45. Okay, let's put it here in the public chat. So first exercise till okay, and then we do a break, and afterwards we go for the second exercise, and then we discuss at the end the outcome. Yeah, if you're not able to fulfill all exercises, don't worry. They might, at least in the second exercise sheet, they might be more difficult to do it in short time period. Okay, have fun, and see you soon in a minute in the breakout rooms.